Our aim is to consolidate our understanding of the interpretations of what the derivative does, both algebraically but especially graphically, and also from there we're going to come up with a method for finding the equation of a tangent to a curve at a particular point. Now the derivative is, and regardless of what notation we're using, f dash of x, dy dx, y dash, d dx of a function, basically it can be interpreted in many ways and it has many meanings, one of which is the gradient function. So if you take the derivative, you get the derivative of a function, and you get another function, and what you get is the gradient function. It's basically a function that describes the gradients of the original function at various points, at various values of x. Now in a minute I'm going to come back to this one and use some graphing software to show that. We can also interpret it as the gradient at a point on a curve, and that means if it's the gradient at a point on a curve, it's the gradient of a tangent taken at that point. We've seen that before. Okay, so some of this should certainly sound familiar. In fact, all of this so far should be familiar. Now, I've just mentioned tangent there. That's why we need the equation of the tangent, because the tangent is very significant, and that will segue us to the second phase of the video in a few minutes' time. So another interpretation of the derivative is the instantaneous rate of change of a function at a particular point or at a particular time. Depends what the variable is. At a point. Okay, so instantaneous rate of change, we've looked at that too. And basically, for example, if we had a distance time graph, and we've seen some of those in our work, so we have, let's say we've got displacement there, and we've got time there, and we've got some sort of function. Basically, the derivative would be the velocity at all those given points. So at this point here, we take a tangent and we can find the velocity by knowing the gradient of the tangent. Okay, and likewise at other points too, each of those gradients and the values of the gradients of those tangents represent the velocity if you've got a displacement time graph. Okay, so because it's the rate of change, so at one point it's the instantaneous rate of change. Another way of saying that is the gradient of the displacement time graph is the velocity. If it's curvy like that, you'll need more advanced methods to analyze it, and that's why we do calculus, and that's why we find the derivative. So we're using a website called Interactive Maths, or intermath.com. Okay, and it's quite good, so I'd recommend you check it out. But in intmath.com, we're going to look particularly at a graph that you can change the parameters on, and it shows basically how the shape changes when we're looking at the gradient function. Let's have a look at that. You might be able to see that we have two graphs there, and we have chosen one. If you look closely, that's an x squared graph, and that's a quadratic, isn't it? So when we got a quadratic, let me just get a better color than I had last time. That didn't work too well. Basically, that's that graph. If you can't see it, it's y equals x squared plus, or sorry, minus 10x minus 1. So that's a quadratic. And you can tell by that parabolic shape. And what we can do is have a look at its derivative, which you can see to the right. And its derivative is linear. It's a linear function. So we take the derivative of a quadratic. Yes, we do get a linear function, and you've been able to work that out. And so the shape goes down by, with a polynomial, by one order when we look at the derivative. And you can see that if you can see my cursor, the slope is 5.3, and the value of the gradient at that same time is 5.3, because dy dx is 5.3. So here, if we go down to the bottom, the minimal part, the slope is 0. And did you see where the little dot here on the derivative, see where it goes when this gradient is equal to 0? Ready? It's going lower, 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 lower. So it's 0. It's on its 0 on the y-axis. So from here, the slope is negative. If you look on the parent function, okay, the gradient of the tangent is negative, and have a look on the right-hand side. It's in the negatives on its dependent variable. Now it's positive. Okay, it's increasing in a linear fashion, and now it's decreasing in a linear fashion. So that's why the dy dx is the gradient function. Alright, so the gradient function of a quadratic is a linear function. What about if we go up a cubic? So we have a cubic. Cubic gives a quadratic. Okay, and we can see there are two turning points, or there's a maximum there on the original graph. And look at what's happening on this graph when we hit the maximum area. It's going through 0. This one here is going through 0 on its y-axis, not its vertical axis. So in other words, it cuts through the x-axis and hits its lowest point around about there, which means that's its steepest downward part on the original function. And then we hit a minimum here, and the gradient is 0 there on the original function. And look, this dot is the point, tracking point is 0 in its dependent variable, and then it gets bigger from there. Okay, so it's a gradient function dy dx. The derivative is a gradient function. Lastly, going up another order. Okay, so you can see it's the same thing. A quartic, x to the power 4, gives a cubic as its derivative function. So I've set up the same thing in Desmos just there, and you can see that I've got a slider bar, n is 4, so that would be an x to the power 4, okay, which is the red, and its derivative is the blue. And as I change that down, we see the same thing happen again. 4 changes to a 3. And we can see that a cubic gives a quadratic gradient function because it's the derivative. And if we take it down another one, if the original one is a quadratic, then we have a linear function for its gradient function. Now I don't think it's going to cooperate with me on the next one. It should have drawn a line. Now we've got a linear function. A linear function has a constant gradient, and it's not drawing it in. I wonder if you can tell me why that is, because it's telling me that it's 1, telling me there that it's 1. It's evaluating for me, but it won't plot it for me. So it should be plotting something like that. Maybe you can let me know why that is, if I've overlooked something, but that's what should be happening. Lastly, if I knock that down to, now we can have n equals 0, that'd be x to the power 0, which is 1. And that's constant, that will stay as 1, so its derivative is 0. See, the derivative of a constant is 0, you can see the blue line tracking through 0. So this idea of a gradient function and the gradient of the tangent is very important. Let's do an example. Find the equation of the tangent to the curve y equals x cubed plus a half x squared at the point x equals 1. So what we need to do is take the derivative. So choose your notation. I'm just going to say dy dx, differential notation, Leibniz notation, Leibniz, and basically it's 3x squared. Now we've got 2 times a half, which is 1, and then x to the power 1. So it's 3x squared plus x. And now at point x equals 1, you could write it like this if you like, as far as notation goes. So you could put a little subscript x equals 1. And so we sub that in, 3 by 1 squared plus 1, which is 3 plus 1, which is 4. So the gradient of the tangent at that point is 4, because the derivative at that point when x equals 1 is 4. So what about the equation of the tangent? Now, important, what sort of line is a tangent? Well, it is a straight line, a linear function of its own type. It's a straight line. So we are looking at y equals mx plus c for our final answer. There's a couple of ways of doing this. We could use the point gradient form of the straight line. So y minus y1 equals m x minus x1 is one way we can do it. Or you could just substitute straight into y equals mx plus c. Now, regardless of which of the two methods you use, we need to find a point that is on the tangent. We need to find a point on the line. Now we've got x equals 1, so we're going to use that. So we've got a point x equals 1, so 1 comma something. Now what's going to go there? Well, if you think about it, a point we know about is this point of contact between the curve and the tangent. That is a shared point, because that helps define what a tangent is. Now we're going to use that. We don't know the gradient of the tangent yet. That's what we're trying to find. So we can't sub it into there. We need to sub this value of x into this original function, because it will tell us also where that point is. So we sub in x equals 1 into this equation. So we have the point y equals 1 cubed plus a half times 1 squared. So that's 1 plus a half, which is 1 1/2, or 3 over 2. So we have 3 on 2, and if we're using the gradient point gradient form, that'll give us the x1 y1 that you see in the formula. And so we go y take 3 on 2 equals m. We work that out to be 4. Outside of x, take x1 is the 1. And so we've got y equals expanding 4x take 4. And we have to add 3 on 2 to both sides to get y by itself. And we get y equals 4x minus 5 on 2. That's the equation to the tangent. At x equals 1. It will change, of course. The other way of doing it, this is optional, you don't have to do it both ways, but the other way of doing it would be using these 2 points, the coordinates here for this point, I should say, for y. So y would be 3 on 2, m we know is 4, and x1, which was 1, goes in for x there, plus c, and we have 3 on 2. Now that's 4 times 1 is 4, okay, and that would be 8 on 2 plus c. So we have negative 5 on 2 is c. So let's write that out. Y equals mx plus c is y equals 4x minus 5 on 2, which is what we got just before. So that's how you get the gradient of a tangent at a point.